Hello everyone, I'm James Tyerman, Head of IT Development at Affinity Water.
Hello everyone, I'm Asen Stoimenov, Data Scientist at Affinity Water.
And today we're really excited to share with you some of the work we've been doing recently using ArcGIS and artificial intelligence. We're going to speak to you about how integrating open source technology and the ArcGIS tech stack has enabled us to target two of our main performance commitments: leakage and interruption to supply. We've been able to achieve some incredible things with the technology and hope that with further collaboration within the industry, we can achieve even more. We would love to hear any feedback from you. So let's get into it. In AMP6, Affinity Water achieved the largest percentage leakage reduction in industry of 15%. Moving into this AMP, we are targeting a further 20% leakage reduction by 2025 and recognizing that what got us here won't get us there. We need to do something different, so we've started looking at our technology and our data and how this could help us solve the problem. Let's get into the solution and how we chose to tackle these objectives. We started with building a platform called Situational Awareness using React and Node.js. The main purpose was to join all of our disparate systems together, such as the pressure and flow reporting from our loggers on our network, works management tools, vehicle tracking, customer contacts. The one thing that pulls these systems together is the geography of each of these. So we chose ArcGIS, and more specifically, the JavaScript API, to achieve this objective. We started by consuming a map layer through the API, and then using the inbuilt layers from ArcGIS to display work orders, vehicle location, and more importantly, the pressure and flow loggers. However, this alone was not sufficient enough. We had to build an alerting mechanism that would tell us when we had an incident or when there was leakage on our network. This is where the AI comes in. Now, I won't pretend I know how that works, so Asen will take us through that in the demo shortly. Bringing the Smart Network Event Detection System, or SNEDS for short, and the platform we have built allows our network control desk and our operational teams to get a head start on our response to incidents and leakage. Let's show you what it looks like. This is a dashboard that the network control desk would see. It displays all of our network DMA in black boundary. It also has all the alerts on there. So the red warning triangles, the yellow warning circle, and the telephone, which indicates a high amount of customer contact. This is our demo environment, so don't worry, we don't have a large problem. We're also able to see the number of vans on our network currently, and we're also able to see the number of loggers, allowing us to drill down into each of these areas without including an incident. Just turn those off. Going to the logger alerts page, this shows from SNEDS the most high probability indicators of an issue, an incident, a burst on our network. So you can see where it thinks the issue is. There's a little red line on the graph on the right hand side. There's also a probability helping our users identify the most important incidents on our network. By clicking on an incident, the user is able to see the flow or the pressure in much better detail, add comments, and add statuses. They're also able to see the time since the alert was raised. By clicking view, it takes the user to a much more detailed view within the ArcGIS platform. You can see here the DMA surrounded in a red boundary along with the loggers. If I just enable the visibility of the loggers on the network, we're able to actually click on each individual logger where it would display its own graph, so we can check across the DMA and how much of the DMA is impacted. We're able also to see other layers such as Maximo work orders or valve ops that may have happened in the last 2 weeks. This helps the user identify what may have caused the issue. The same can be said for turning vans on. If there is a team within the area, then they're able to contact that team by clicking on the van, getting their details, and we're able to see if they're doing anything in the area that might be impacting customer supply. You can also see a breadcrumb of where that van has been within the last 24 hours. This also refines it further. Moving on to leakage, we're able to report overnight any outbreak leakage. Similarly to our bursts, it displays a graph on the right-hand side showing water balance though, not flow or pressure. So we're able to calculate our water balance per DMA in real time. By clicking on the alert, again, it takes them into a more detailed view. Here they're able to add a meters cubed increase, a work order number, or flag it as true leakage. This helps the model learn and make it much more accurate. We're also able to provide further probability. Acoustic suggests that an acoustic log on our network has also validated the leak. There's a weather percentage, so how much the weather might have affected it, and a similarity percentage, so have we had anything similar that has been validated as leakage previously. This concludes the demo for the Situational Awareness platform. I'm now going to hand over to Asen, who can take you into more detail around the AI.
Hello, everyone. What we'll talk about today is some of the more exciting stuff in the industry surrounding leak location and how to get leak location insights based on data science framework and machine learning modeling. Before that, I just want to touch on SNEDs and what you've seen so far, the models behind the logger alarms that are informing network control desk and the leakage teams about operational events day to day. So these models are classification models. They're trained on previous burst data where we find out the earliest point where a leak or a burst event is obvious, and the models therefore find that point in the future where the operation teams look at and react in the earliest possible stages of bursts. These are, as I mentioned, classification models. There are about 20 dimension models, and the main technique used to model them is XGBoost, extreme gradient boosting. So let's move on to leak location. So there are a few important components to leak location and a few important steps that we decided to take as a company. Anyway, so the first one is we want to represent all the geographical and logger data in terms of graphs. So what that means there is that each pipe, for example, you can see here there's the P's, there's the pipes, and there's the T's, the junctions. And there's just an example. But what you can include any asset on the graph, and each asset will be a node, and each node is connected to one or more other nodes, and then each next node is connected to one or more other nodes, as the definition of the graph is. So what this enables us to do is to traverse the graph network very quickly and with popular algorithms such as breadth first search and depth first search. And then on the other hand enables us to declose the different paths between the loggers and burst events, and the interaction between those and various other assets and geographical insights on the way. So as a next step, here we append the geographical context to each node, to each asset. So if you have a logger, if we have a pipe, then they're in certain sorts of each certain type of soil, they have certain type of altitude. So some of the data that we append to each node as a context, it includes drift geology, ground moving, shrinks and swells, corrosivity, soil classification, solid geology, and we use digital terrain model image to get the altitude. It's much more accurate than a contour because it's many more points on the DTM to get the most exact altitude possible for each asset. So that enables us to extract features to really bring all the data into a data science dimension, and it's to bring it into the familiar format of X and Y, which is independent versus dependent variables, etc. So some of the features that we extract from here is we model, as part of this, we can model the pressure and the flow in pipe, like which direction is the pressure, which direction is the flow, what's the exact pressure on this particular pipe versus that particular pipe, even if there's no log around there. And we also can see what the soil is, when the water is kind of going up here, where it's going downhill, etc., etc. And then finally, after we have our X and Y, we can build the machine learning models. And the way this is done, let's just skip to that. Okay. So, of course, the way that it's done, we look at the sensor insights in terms of the features, and we relate them to this context that we just spoke about, so that we know that how, when the sensor reacts, which we know every 15 minutes, how all the sensors are behaving, we know like what's the context, what kind of insight, and we can then predict the leak location by using our machine learning models. And the first iteration of these models included a blend of two machine learning models. So it's one classification, one regression. So the classification model is an XGBoost model, which predicts the probability that each pipe has in the DMA to be the burst pipe. And on the other hand, we build a regression models using support vector machines to see what the average distance is between what the logger shows and what the actual event is. So you can see on the map there's a DMA and there's two loggers in blue, and then we have the burst event in red. And we can see that on this occasion the predictions occur quite well in terms of distance and probability pipes. So the final output is just a blend. So the pipe probabilities are overlaid with the distance, and depending if they match the distance, the probability is reduced or increased. And the gray pipes are pipes with no probability assigned, where the model thinks this is no chance, basically, for the burst to be there. And by aggregating the outputs of the model, we can see that there's saving that we can make. We can get the technicians to the leak location faster, and of course we can fix the burst faster, saving us additional costs in water and other types of costs. And that's pretty much it really at this stage. There's a lot of work to do on that, and to improve it. It's a very high dimensional problem, and it requires a lot of attention to detail to make sure that the machine learning models are trained with as little bias as possible. But we can see that there's very, very great potential in that, and we're very excited about working on it now and in the near future. Thank you.
Thanks, Asen. So hopefully you can see how powerful combining the two technologies together are. We're really very excited around the possibilities that this technology can provide. We've seen from the tech that we have had a reduction in response times, with an opportunity on each incident to save over an hour and a half. Further benefits can be seen in reduction in time taken for leakage to be found. And also, all of our systems being visible in a single geographical view is invaluable. Using Esri's utility network editor, we are starting to look at automating modeling so that we can initiate any modeling straight from the field, allowing real-time decision making and quickest possible resolution. We're also looking at building a digital twin, a software-defined version of our production and distribution network, giving us a sandpit environment, allowing us to simulate and replicate real-world scenarios to inform a better outcome. We hope you've enjoyed this presentation, and we look forward to providing further updates in the future. Thanks.